or is it right? It's just here. These are both listed here.
Right. All right. So this is part 2, week two of compiler. So I'm just recording that. So I wanted us to look at symbol table quickly. The symbol table you're going to build for part lab 1A, it's just a symbol class. It just doesn't have to have all this stuff yet. But a symbol, it's just any user-defined name as a symbol. Variable name, function name, type name, constants, class name, method name, any ID you use in your program is a symbol. Usually, these are the information we care about. A symbol, name, what is this name? The type, and we won't have this type information yet until we get to the parser. The use, sometimes you tag these with just a constant. So 0 is a variable name, 1 is a constant name, type name. Okay, you just use, right? You design, whatever numbering scheme you want to tag these as a use. So my pound defined symbols are constants. So right now it's all I'm going to use it for, but I may tag it. Okay, this is a constant with a value. A variable name, I don't store the value in the symbol table. Variable name changes its value as it goes on the stack in the execution, right? The dynamic execution stack. So I don't actually store the value of a variable name at compile time because I don't know what its value is most of the times. Sometimes I can't, I know, because I'm just assigning something to it. But if I do a CN, I have no idea what they're going to type in, and I don't care. I just care that I have this statement here. I just care I have a variable name, so I have to use it and say, yeah, did I declare? Yeah, we did. Is it in the same scope? That's where the scope comes in. Okay, so value is really just for value of a constant. All the other values, they dynamically change in the program. I don't store it at compile time, yeah.
And that's where you got the type and the use. Could you use like a enumerated type for that?
Yeah, definitely. Yeah, we use enumerated types a lot in compiler, writing a compiler, just because it gives me a meaningful constant that I can work with, but also gives me a actual associate.
I don't understand what the value is. It's constant.
It's a constant, right? So max is 5, right? So it has a value of 5.
So then everything else like an int or double, those would all just be like some arbitrary number. You don't really care.
Yeah, doesn't matter. Mm-hmm.
Now, is that something that the analyzer puts in then, the value of the constant?
The preprocessor, actually, yeah. When you say pound define max 5,
Okay,
so max goes in there, 5 goes in there, right? The lexical analyzer doesn't actually put anything in the symbol table because it doesn't know what it is.
I was thinking, keyword.
Oh, keywords. Oh, no. Yeah, so it doesn't actually know. So there's scope. There's also stuff like lifetime. So if you have static variables in C, and a lifetime is for the duration of the program, but the scope is within the local, right? The curly brackets. But when you say static inside of a function, that thing never goes away until the program goes away. So symbol table might want to know that. So it can, when it generates code, it actually needs to go to symbol table and figure out some of this information. So the key here is, after I read my file once, hopefully, without having to read multiple times, the one pass compiler is the most efficient. If I'm constantly opening a file and reading it, it's going to slow me down. So the key is I read through my file once, .cpp file, .h file, whatever the file might be. Actually, .h file is not compiled. .h file gets included. .cpp file, say, I'm going to capture as much information, all of the necessary information I'm going to need somewhere. So when I do anything else with this file, I have it. So that's why I have a tokens list. I have a symbol table. After I parse, I'm going to have a parse tree or some sort of parse data structure. So when I do my semantic analysis or code generation or anything else, it's out there. Okay, so that's kind of our goal. So keep that in mind. Anything we do, how can I minimize, having to go back and go, oops, I didn't get that. Let's go back and see if I still have that information. Right, so assuming that as soon as you read it, it's gone, right? You're not going to see it again. So for part one, we're still going to talk about, so what should a symbol data structure or have? Okay, each symbol should have a name and a value for now. If you're going to create a class, it needs to have a string for the name and a string for the value. We're not going to keep track of what type of value it is. That's not a what pound define supposed to give you. Pound define has no type. Right? You say max 5, it's just a quoted 5 string substitution. So if you gave me something weird, and I'm just gonna, well, after pre-process, I'm gonna get something weird. For instance, get a forecast to see. If you say pound define max to be XYZ, okay? Then you say x equals max. Well, what you're going to get back is x equals XYZ. Literal substitution. It doesn't know what XYZ is. It doesn't know if it's a variable that you should have defined, declared. It doesn't know anything. It doesn't do type checking. Right? It just says, okay, you want max to be XYZ? I'll put XYZ in there. Right? It's not a string. It doesn't have quotes. It's just literally those 3 letters. Take these 3 letters out and put these 3 letters in. That's it. That's all pound define does. It's syntactic. It doesn't know about syntax. Doesn't know anything. So similarly, if you say min equals 5, and you turn around and you say, oh, min equals 10. Well, what you're going to get is 5 equals 10 semicolon. Right? You wanted min out? Okay. You want 5 in? All right, I'll put it in. Okay. Who's responsible for that error? Well, it turns out it's not lexical analyzer either. Lexical analyzer says 5. Okay, your number token, you go. Equals your token, you go. 10, your token, you go. Semicolon, you go. They're all stored in your data structure. It's the parser that came along and goes, what do I do with this? I got a number equals number. That happens to be a constant. Constant equals a constant semicolon. They don't, well, even if they match, I don't know what to do with this. There's nothing in my language that said I could have 2 constants equals assigned to each other. Right? There's rules about the fact that they're constants. I can't take the 10 and put it into 5 and make the 5 into a 10. Where is 5 stored? Well, 5 is stored in the constant static section of my memory. And that's where the memory stuff comes in, right? Where are these things actually stored? What does that actually mean? Right? Where is x stored? Well, x is on the stack. So if I say x equals 10, okay, I can put 10 in the stack location, right? But 5 is a constant, 10 is a constant. They get their static region. I can't change the static region at all. Right? So a pound define doesn't care. It's just, okay, you defined it. I'm going to do literally yank these things out and put this thing in. Right? So when you put this information in the symbol table, max is the name of the symbol. XYZ, quote, XYZ, a string, is the value of that constant. Min is the name of the symbol. 5, quote, 5, is the value of that symbol. So in part 1C, when we go do substitutions, we're going to yank one out and put the other one in. Yank the symbol out if is defined in the symbol table, and put the other thing in. Just substitute it. Okay, that's easy. So think about it, it's really easy. Pound define is like the easiest thing you can write. Okay, I mean, if you're going to do a global search and replace, you're done. Okay, except we're not exactly doing a global search and replace. We're actually pulling these symbols out. It can get a little complicated because you can define a constant more than once. You can define max to be something, do a bunch of things with max, and then pound define max again to be something else. Then anything after that is this something else. Okay, so we're not going to worry about that case. Right? So we're just going to just say, okay, yeah, most people, unless they really want trouble, most people put all of their constants up front, right? And then you don't have to worry about it. So how do you test part 1A? So I want you to build a symbol table. So each symbol is a name and a value for now, and we're going to add types and stuff later. So make sure you can expand on that class, that object. And what should be the container object for these symbols? Like I said, we're not going to have a million symbols. I don't want to optimize for searching. I don't want to, I want to optimize for insertion, not necessarily searching. If you're going to do a balanced binary search tree, because to minimize for, optimize for searching, that means when you insert a symbol into that tree, you're going to take a lot of time to figure out where it goes, how to balance it. Does everybody know how to do a balanced tree? Okay, how to balance it. So each time you insert something in the table, it takes a little bit of work. You may have to rebalance the tree. Okay, well, how often are you going to look up that symbol? Again, we're maybe dealing with a handful of symbols here, or maybe even hundreds of symbols, but still not any magnitude, right, that we're going to really worry about. So if you just have a list as a container because it's dynamic, or vector, which is actually a growable array, dynamic array, STL, vector, or write your own. You know, if I'm going to say, well, I'm just going to have an array of symbols. How big should that array be? Okay, you're going to waste a little bit of space, but you're probably not going to hit 2,000 symbols in a typical program. Okay, so of course, if I'm writing the C++ compiler for Microsoft, I'm not going to limit them to 2,000 symbols. I don't know how big a program you're going to write. I don't want it to like run out of symbol space. So I'm going to use some sort of dynamic structure. For your lab, you're not going to hit 2,000 symbols. You're not even going to hit 100 probably. If you're lucky, you have a handful of symbols. That's it. Okay, so any sort of container is fine. Right? We're not even going to worry about hashing or about tree or anything like that. So just make sure that you can insert something into the table as a test. So 1A, you're going to write a class for the symbol. You're going to write a class for the symbol table with a container of the symbols. You have a main function that says, okay, I'm going to insert something in, max 5, min 10, whatever. Okay, put something in, okay? And tag those as constants because you may have integer and you may have variables later, but we're not going to worry about tagging them yet for now since we only have value and name and value. Search for, do I have a max in there? Well, depending on what kind of container you have, a list, linear search, vector, linear search. Okay, we're not sorting it, so we're not going to worry about binary search or anything. Delete a symbol, yank one out. Okay? If you're using STL, all of that container management is done for you. You don't have to worry about the data structure, getting things in, getting things out, searching. That should be fairly simple. So 1A should be really quick. You can probably just do it tonight. Right? I mean, really, it's just you'll be doing it while I'm talking. It's really easy. Okay, so that's not really a big issue. So if I have these things, I think last year I actually had the students do more on the preprocessor directives, but that's okay. But say if I have pound define max 50, or max goes in, 50 goes in, pound define some symbol goes into the table, pound define some symbol again, you can redefine the symbol. So if it's already in your symbol table, just replace it. N-define some symbol, yank it out of the symbol table. We're not going to do N-define, but yank out of the symbol table. Pound define min, gets an entry in there. If you pound define max to be 100, max is already in there. Just yank out the value 50 and put in 100. You only have one, with pound define, you only have one symbol. Right? It doesn't matter how many times you defined it, only goes into the symbol table once. Okay, so this pound define stuff is part C of the lab. You actually have to process this. For part A, just get a simple table so you can insert, delete, and search. Okay, so that should be fairly simple. Now I'm going to actually look at the code. Well, we're going to look at the code. Okay, so I'll come back to this. Can I come back to this too? Okay, part B. Part B. This is what I have from the last term's lab, right? I have all these tokens, right? Now I have a simple table take class. It kind of sits out there. Now part B. First thing I want to do for part B, which I did not do in last term's lab, was // comments. You can have different comments. If you have a different language, you may have an apostrophe comments or whatever the symbol might be. I'm not going to worry about the block commenting like C/* and /*/. Okay. You can do that too. I mean, basically, it starts with the /* and then grab anything that's not a */ right? You can do that if you want, but just a line is okay, like // comments. If that was in your source, basically you read that line. It's almost like processing a token, right? You read that slash, and you read another slash, and you go, everything else in that line is gone. Well, which means I still got to read everything out that line until I hit the new line. Okay, ignore that whole thing, gone. There's not a token, right? So many of our classes, we told you to write, nice documentation, nicely formatting stuff. One of my colleagues down in Klamath, he's very strict about formatting your code. Make sure they're readable. Oh yeah, they're readable for you. Compiler doesn't really care. All of that nice formatting just gone when the compiler gets it. Just tokens. It's like, I don't need formatting. Okay, so comment, just simple comment like //. Okay, so again, how do you modify your lexical analyzer to take care of that? Treat that as a token. You have a / token, and then just yank that token out. Right? Don't save it into your list. Okay, so everything is almost, it's little these mini machines, right? Little DFAs. Well, this happens to be a DFA that starts with a slash, and then everything else. Till you hit the new line, then it's gone. Okay, so part 1B, one of the things for one is that keyword table. So I have everything as tagged as ID. Well, I might want to put in all the keywords of my language. I just type in something I could remember for C, right? It doesn't mean you have to support all of this. Or your language might be different. You might have something I don't have. That's okay. Right, so do while loop, I don't have a do. Okay, but say this is my keywords. Could just be a static array, static table. Okay, then when I hit the int, I'm going to look. Do I have int? When I have main, I'm going to look. Oh, no main. Main is not a keyword. Main is required, but main is not a keyword. Int, yep. X, nope. ID, X, no. ID, XID, max. Okay, so before this, well, we still haven't processed the preprocessor yet. So max, nope, it's not a keyword. ID, return, keyword. Okay, so that means for every single ID you found in your machine, your lexical analyzer, check it against the keyword table. Let me just do it quick. If you dump this keyword table into some sort of STL container, just call search. Easy. Okay, so again, it's static. I'm not saying you have to put the word static. I'm just saying this doesn't change. So it can be hard-coded into your program. And your program only parses your language. We're not writing a generic parser that parses through everything. We're parsing your language. So it's okay if it's just hard coded for your language, right?
Yeah, we want to do and they probably do the preprocessors first before they do this.
You could do the
Because
reason.
you want to pull out all the, because if you have a preprocessor that says like a capital int is equal to a little int, because you're trying to make it so it's.
Oh, that's a
You know
good
what I'm
point.
Yeah,
That's
so
a
you
good
wanna do it
point.
So that then when you did this lookup, you would find the int.
Yeah, that's a good point. Yeah, that's a good point. Yeah, that's weird, but I mean that's probably not. I mean not a good
Or you do a double
programming
pass.
practice. Yeah, you could do a double pass. So preprocessor is one pass, right? Lexical analyzer is another pass, right?
Okay.
So yeah, that's a really good point, Ray. So Ray is saying, well, if you actually pre-process and inserting some keywords in, and then you got to go look again, what you do. And in fact, even with the number 5, I don't know that that's actually a number. So I'm actually have to determine if 5 is actually a number again, right? So
Yeah,
If you were to do the preprocessor first, would you risk replacing a preprocessor statement where it shouldn't be replaced, like in a string? Like if you haven't determined that that's a string yet, and you go and replace all your capital INTs, lowercase INTs, and that's
Yes.
somewhere in a string,
yes,
then wouldn't that
yeah.
mess that up too, to where you
Yeah.
have to do a double pass to do it right?
So that's a good point too. So I did have I think I have a slide coming up. So and that's why I actually had to do the lexical analyzer first. So the preprocessor basically does a lot of the tokenizing as well. Okay, so David is saying, what if you have a quote max? Right, then I don't want to change the max into anything. I mean, my quota string, that's my string literal, which means your preprocessor has to be smart enough when it hits a quote and knows, okay, anything else after that belongs to the quote and not a separate ID. So it actually does have to like recognize what those tokens are, which is, so that's why they really kind of work together, right? But if there are separate processes, then the preprocessor has to do some of that tokenizing anyway, right? So it's really is 2 different processes. The very first C++ compiler that is called, actually is just a front end preprocessor, which converts everything to from C++ to C, and then C takes over. It was a very, very slow process. It's called C front, which process everything C++ stuff and make it into C. And then C++ got so complex that they couldn't do that anymore. So they had to build a separate compiler for it, which actually was a lot more optimized because the C front could take like minutes because it has to figure out what to do. It's like, okay, what is these classes? And okay, we don't have that in C, so how did I make it into C, right? So, but that C front basically is a compiler. It has to do all of that processing anyway. So, so then sometimes they do go together, or at least they're pretty seamlessly. You don't know which part was the preprocessor, right? And then the lexical analyzer kind of takes over. But yeah, in this case, if we're doing it this way, we do have to go back through and make sure whatever we replace, okay, do we just replace a keyword, or do we just added a number, or what was it that I just put in? Because I still have to tag it and say, yep, okay, what is that thing? Okay, so the keyword searching should be, let me just check it against the keyword table. This keyword, tag it as, say that's a keyword. Also, I want you to kind of tag and store the type of these things. So instead of just say, oh, that's a symbol, yeah, that's, I actually put if it's an int, then I know it's an int. It's a keyword, yes, but more specifically, it's int is an int keyword. If is a keyword, but more specifically, it's if. So when I look at my grammar later, bunch of statements, what type of statement could I have? Well, you can have an if statement. What does the if statement start with? It starts with an if token. So if I have an if token, I know, okay, I'm on the right path. I'm going to see if I have an if statement. So I want to tag them as what they are. Similarly, greater than sign. It's an operator. logical operator, yes, but it's also just greater than. So instead of, so the tag field, or the, I call it, actually call it type, or call it whatever you like. So the name of the token is the string, the int, the main, the quote, okay, and the type, or what type of thing they are, basically it's just the name, except for IDs and numbers. Or if your grammar requires like lumps, int and double and everything into, just say, oh yeah, you're a type, then you are a data type, then the type of that thing becomes the data type. Okay, you see what I mean? So if int, nowhere in my grammar do I see int. Instead, I see the word data type. Then I want to tag int as a data type, right? So, but if in my grammar itself, I'm actually using int and double and char and everything else, then I want to tag that. So whatever this tag is matches whatever I have in my grammar. So if my grammar, I call it identifier instead of ID, then I want to tag this thing as an identifier, right? Or in my grammar, I call a user-defined name instead of ID, then here I want to say main is a user-defined name. So when I'm looking at that token, trying to match with my grammar, what does my grammar need? User-defined name. What is main? User-defined name. Okay, you're it. Okay, otherwise I'm going to have to do some thinking. Oh, user-defined name, is that same as ID? Okay, what is it? Okay, so just whatever is in the grammar, and in fact, you're going to write the grammar later. So whatever you use here, that goes into the grammar. If you use ID here, ID goes into the grammar. Right? So it kind of was progressive. So we determine what actually goes into the grammar. Homework 2, you actually have to write out your grammar before you can write a parser. So, and then you can actually work on this lab together. I mean, it doesn't have to be 1A, 1B, and 1C. You can work on it together and goes, yeah, I just did it. Okay, I'm just going to turn it in. Okay, that's fine too. Okay, I'm just breaking it up into smaller pieces and hoping that will be easier, especially for some of those that are joining us this term. You don't have that lexical analyzer yet. You definitely want to get those pieces in. So part C then is you're going to read your list of tokens. If it's a pound-defined token, you're going to yank it out. You're going to read it, process it. How do we do that? Well, if it's a pound-defined, first of all, I got to get rid of your comments. Okay. Then if you have a pound-defined line, we're going to yank it out. We're going to read it and insert the next thing, which is max, into the symbol table. If there's a value associated with it, it may not. If there's a value associated with it, put a value into the symbol table. First of all, make sure there's no max in there already, because you can only define the symbol. You can multiply define the symbol, but they only get one entry in the symbol table, right? And keep reading. Every single token, if it's an ID, is it in the symbol table? It's a constant. Main is not. X is not. Max is. Then yank out max and put in whatever the value is. Or if there's no value, then it gets an empty string. Okay? If there's no value, that means max is gone. You just get an empty string there. Again, we don't care about syntax yet. We don't know about syntax yet. We have no way of telling what the syntax should be yet. We're just doing a preprocessor. If you told me max should be nothing and you put a max there, I'm just going to yank out the max and call it nothing. Okay? So
Symbol table only work with pound defines, pretty much.
Symbol table in our purposes, yeah, it works with pound defines right now. Oh no, just for our lab. But symbol table also works with this x later, okay. Int x. Okay? We assign like the x equals 10. When you say int x, x gets put in the symbol table, and then with the type. And then when you say x equals 10, it's going to look in the symbol table, see if x is there.
Oh, okay.
Okay, so yeah, we're going to use the symbol table a whole bunch more times in lab 2. But lab 1, we're just doing pound defines. Okay. Every year, I have students try to do the int x, try to put in a symbol table and try to do more. Not in this lab. This lab, we're just doing preprocessor, Lexicon analyzer. What we're going to get out of it, bunch of tokens. Then I'll worry about how to put those tokens back together again into something meaningful. Right? So I think this, Ray, your point about, okay, now I pre-processed. I pre-process everything. So my pound define is gone. Right? My max is gone. I replace it with 5. But what's 5? Pound define did not tell me 5 was an int or number. So that means I actually have to go through my lexical analyzer and go, 5, what are you? You are a number, right? So this process, so what if that 5 was, a keyword? Pound define max to be while. Now I'm going to yank the max down and put in the while. Well, the while is a keyword. Well, that means I have to go through at least that part of the lexical analyzer and say WHILE, what are you? Your ID, but you're really a keyword. Okay, I'm going to tag you as appropriately as a keyword. Okay, so yes, there's a little bit of back and forth here. Right? Because they really do very similar things, but they're sort of, they handle different pieces of this thing. One that just care about the tokens, and the one actually go do some substitutions. And it turns out that the pound define is the easiest preprocessor directive. Preprocessor directives actually are quite complex, right? And things even like we use all the time, pound include. Oh, good segue, pound include. What do you do with pound include? How should pound include be handled? Well, it turns out pound include is, say, I want to pound include b.h, which is my file, b.h. In b.h, or something else. It could be another pound directive, right? Pound include. What happens with that is, so did I say anything with that? Okay, I'm just going to wave my hands here. Okay. The line pound include quote b.h is strike out, it's gone when the lexical analyzer gets it, right? If it would do the preprocessor first, it's gone. What is in its place is the file b.h. So basically opens the file, sucks the content all in at this point. Okay, whatever's in that file gets sucked in right there. Then the preprocessor continue to process because look, b.h has a pounding define. Okay, so it continues to process. It could have another pound include, then in which case it needs to go open up that file, which has another pound include, which goes and opens up that file and sucks all the content in, right? I'm still like not quite done with this first pound include yet. I'm still like keep opening files, okay? And that's what I told you last term that Microsoft finally said, I'm not going to keep track how many, circular, or if this one includes the previous one, I'm going to go through this whole thing again. So I'm just going to let you keep opening files till you hit a magic number, and I can't open anymore. Sorry. Okay, you have a circular include problem here. Okay, but the file, I should probably open this up first. Sorry, I'm gonna try to find Visual Studio. Or actually, I'm just gonna find my desktop, my Explorer. Yeah. Visual C, include, pound include IO stream. We do it all the time. Pound include IO stream. Oh, really? What? Because, sorry, I'm gonna open up this first. 2012. Okay, I guess it's fine. I have a 13. I think I clicked on the wrong one. Which one?
2015.
Oh, I don't have 15 yet.
Yeah, it's on community. It's free.
Is it community? Okay, yeah, I should put it on there. I don't have it yet. Still using Windows 7 on my desktop.
Really?
Yeah, I don't want to upgrade. I don't like 8.
You can get the Windows 7 theme for Windows 10.
I could. It's working well. I don't want to change it yet. Oh, come on. Really? Sorry. Should probably had this open ahead of time. Slow, slow, slow. Okay. So I'm actually just going to open up that file. I probably could. Get on my, it's okay. Just. When you're, I mean, you can have it just like a 1 line, 2, 3 or 4 line program in main. But when as soon as you pound include, IO string, you have no idea what you're actually including most times. Okay, as soon as you pound include IO string, it opens up this file. Okay, notice it has a bunch of pound directives, pragma. If not defined, define. If not defined, checks the symbol table. See if this underscore IO stream underscore is already in there. If it's not in there, pound define puts it in there. Okay, so if not defined this, then it includes immediately iStream. Okay, so it didn't even hasn't got a chance to get down to any of the other stuff yet. So immediately opens iStream. Okay, so one file IOStream opens iStream, if I can find it. iStream, okay, which immediately opens OStream. This file is just getting bigger and bigger, right? It's recursive. It's recursively opening up stuff and processing them as you're opening them up. I am still on like line 5 of IOStream. I haven't gotten any further than that because I immediately jumped to iStream, which immediately opens up OStream. So I'm still hanging over there. That's why it's recursive, because I don't know how many times I have to keep going, which immediately opens up iOS. Okay. Not sure if this is entertaining for you as it is for me. iOS, which immediately is open up. Okay, you get the idea, right? IOStream actually has like 7 or 8, 10 different. Eventually, it gets down to standard IO.h. So there's no magic in IOStream. The C in, C out, everything is built on C's library of IO. Okay, it just is a class, so it gives you, right, methods you can access, objects that handle some of this IO stuff for you, so you don't have to do printf and scanf and worry about the format. Am I reading in an int? Am I reading in a double? Am I printing a double? Am I printing a char? Okay, all that is taken care of for you using like these 10 different files, 10 different libraries, basically. But then all of this text, all of this gets sucked into your main.cpp, all of it, except for the preprocessor ones, and it gets preprocessed out. So all of these classes and functions that you never knew you had, or don't even care that you had, they're all in your main.cpp after preprocessor gets done with it. So if you can actually look at that main.cpp, the preprocessed one. Okay, someone said there was like a flag you can turn on so you can actually see it. I don't know if you care to see it. Why would you want to see this? I can't even read this. Why am I reading this? Okay, but it's all there. Okay, so that's what pound include does. So there's actually doing a lot of stuff for you that you don't really care to know.
Do we want to add that into our program?
If you want to add that to your program.
Or is that part of the lab?
That's not part of the lab.
Okay.
Okay, lab's gonna stop at pound define. Okay, I've done pound includes before. Actually, had students do cycle detection instead of just say open up 2,000 files, you're done, or 10,024 files, you're done. It's actually quite difficult because it's recursive. Right? Because you sort of hang over here until you process this one, and you sort of hang until you process all the way through, then you like come back, right? But I want to tell you that I do want to just like briefly go through these preprocessor directives so you know what they do. If you ever had to write one, you know what pound define does now. So if not defined, looks in the symbol table, defines it, puts it in the symbol table, and then of course with the NF, you do this all the time, and involves the symbol table. Right? Compiler uses a symbol table to take care of this. And I don't like code like this in the preprocessor. Sometimes it's necessary because you maybe add your environment, you can add your environment variables in. So if this same code could be run on different machines under different environments, you can turn these flags on and off, right? But I usually like to do that in the code rather than the preprocessor. But nevertheless, if there was a flag, and I can tell you where to turn this on and off, and depending on the value of this flag, you either have this code, this line, pound define, this line, or, right? So the reason there's no formatting indentation is pound really doesn't like a lot of white spaces. In fact, it didn't allow any white space before. Now it allows white spaces. So the if, if, else, and if, that's the construct. And then the lines, right? The pound define, display, the pound define, those are the actions. So if your D level is 0, that means the only line of code that gets added into your source is pound define stack 0, which preprocessor will immediately preprocess out, right? And add a stack 0 into the symbol table, and that line is gone. But if the D level is greater than 5, that means this line, display, debug pointer, whatever it means, this particular line gets inserted into your source. Your lexical analyzer, since it's not a pound, your lexical analyzer will get it, and it will treat these as tokens. Okay, none of the other lines get in. That's what these pound if do, right? Basically, it's the if statement, but it's at the preprocessor level. D level is not a variable. You have no opportunity to even define a variable yet. It's preprocessor. We haven't seen any variable yet. So how do you actually get D level in? Actually, I think that's somewhere here. No, there, maybe. Okay, so just jumping ahead a little bit. Actually, in the like a Visual Studio environment, you can put in a symbol in the command line. Okay, so IDE really makes your life a little easier, and gives you a nice GUI interface and stuff. But underneath it all is just all command line DOS calls, so operating system calls. So how do I set D level to something if it's not even a variable? Well, that's done through the environment. So you can supply it through command arguments. So you can set, and also somewhere in one of these options, I know it's a little small and 2015 might look different, but in one of the properties page, there's a preprocessor option. In the preprocessor option, notice you say the preprocessor definitions, Win32 underscore debug underscore console, whatever it might be, are constant symbols. Where do they go? They go into the symbol table. Okay, so that, all of these, system level stuff like debug, or is this debug option on or off? So Well, check it. Is it on or off? So somewhere in your code, if you're checking to see if debug is on and off, or does it check, well, it's on the symbol table. So all of those symbols get added to the symbol table, right? Even though, you know, this has always been there. Just you just didn't know. IDE sort of took care of that for you. But that's where how symbol table is used. So there could potentially be a lot of symbols in there that you're not aware of, and that's fine. There's a lot of system stuff. But like I said, we're not really worried about that for our lab for this one. So I want to check the time, make sure we're doing okay. So last year, I did the labs a little differently. I still had the student do the lexical analyzer, but I don't think I broke it down quite as much. So I just say, you know, give me so I didn't really broke it down into like that list of tokens as much. This slide is actually from last year. So you can either have, like I say, you can either have a standalone preprocessor, right, which means it still has to go through a lot of the tokenizing to figure out. Right, so to get a modified source and then feed the modified source through the lexical analyzer, which you should have already, and then get a list of tokens out and then tag the tokens, okay? Or you could you could sort of combine them both, right? So, which is kind of what we're doing. We sort of have the lexical analyzer. Now we're going to add a preprocessor piece, and then really make them work together because they sort of have to bounce back and forth a little bit. Okay, so, but I think you're in a good position because you do have most of you have the lexical analyzer already. You're just adding stuff to it. Okay. And what do we want to get out of lab 1? The whole thing? List of tokens and tag them appropriately so we can feed them into our lab 2, which is a parser. Okay, so when you get out of lab 1, if this was the input, when you get out of lab 1, the whole thing, all 3 parts, you're going to have a symbol table already. You're going to get this list of tokens with those tags. Right, and then we'll just move on. And if you don't have lab 1, can you still do lab 2? Hopefully we don't have to worry about that. But yes, what do you need for lab 2? That file. Right? If you even manually create that file, you can do lab 2. Just need tokens. Right? But hopefully they all work together. So you have lab 1 that produces that file or that data structure for you, and then we can move on. So, all right. I skip over some stuff. Let me double check. So is the lab clear? Let me switch over to the Blackboard here a little bit. Maybe. Oh, for those of you that missed it, the YouTube video for the first part is posted immediately. So I will, usually after class, each class, I'll send out the links to part 1 and 2. So you can, if you need a review, for whatever reason is there. Hopefully you could hear me. This microphone is actually not terrible. Let's just take a look at the assignment page. Make sure I got everything covered, that you have all the information you need to do the 2 short labs this week, getting symbol table, getting the keyword table in, getting the tokens tagged. And then you have the preprocessor part, where you parse the pound define max and put in the symbol table and then do the textual substitutions. Okay. So we're not doing the textual substitutions now in our data structure of the tokens. So we're not going back to the file and change the file, okay? The preprocessor itself is actually changing the file and produce a new file. But now we already got the tokens. Just yank max out and put in the 5. We're not changing it, right? We don't have to change the original file. So hopefully that makes it easier. And I think that was the improvement I did from previous years, which I wasn't clear about where do you actually do the substitutions. So someone was trying to do the substitutions in the file itself. Well, that's kind of hard. I guess you got different length and you got to worry about your file pointers. So now we're just doing the substitutions in the actual token, in the actual string. So, okay, so the syllabus is on the Blackboard. So if you register for the class, you should have access to it. I have the previous slides from notes from previous CST 229 grammar class. This might be from the year before, so it's similar, should be very similar. And then the lecture notes right now just has the big lecture set from this today, right? The 2 weeks. All right, so what's posted for assignments? So lab 1 is just a simple table. Okay, that's due Friday, Saturday. Saturday, right? 16 Saturday night, midnight. Okay, so, but if you can get it done early, get it out of the way. So this lab, you need to use the lexicon analyzer from 229. If you don't have one, catch up and do one. You read in the, so you add a keyword table and then tag the tokens. Okay, so pretty straightforward. All right, so this one, we want to do just some more details later, or I should provide the details. I did provide the details in the slides. So we want to list the tokens with the preprocessor directives removed and processed, also adding the comments and remove the comments. So you can at least get to do that. And if you really like to work ahead, since we're not meeting next week, if you like to work ahead, after we have the tokens, then we need to worry about, okay, how do these tokens fit together into the structure of the language? I think you'll like lab homework 1. Homework 1 is, I like you to draw. You can hand draw this. It doesn't have to be nicely, formatted, electronically. Just hand draw this and scan it and submit it. I want to give you a grammar. And then I'm going to give you a program and ask you to match up. Now we're dealing with the real grammar. We're not doing the A's and B's and C's anymore. Now we have a real grammar. Then we have a program. And how do you match them up? What does it look like? What does that parse tree look like? We know what the parse tree look like when you just have S, A, and B's and C's, right? Okay. But what does a real parse tree look like for a real program? And this happens to be Pascal. Okay, make it bigger.
Bottom right.
Bottom,
Maximize your windows. It's not really a taskbar.
this. Okay, there you go. Okay, so you'll have this. So if you can't quite see this. Okay, so this is a small grammar for a very small subset of the language Pascal. A very small grammar. There's leaving out some stuff like type only has integers and real. It doesn't have char, doesn't have any of that. It's very small grammar. The bold, the ID, you see the ID here? ID, the program, the var, the function ID, those are the tokens. But those are the token types, like ID, program, whatever, right? So, well, I just need the ID here. I don't care what you call it. Right? The open paren, the close paren, the semicolon, those are all tokens. Those are where we're matching. So you have a list of tokens. Now we're going to match them up. Okay? Don't worry. I'm sort of jumping ahead a little bit if you like to work ahead. So when you come back week 4, one of the first things we're going to do is we're going to take a small grammar and a small input and then do a parse tree and do this matching, okay? And this is not due like till the 30th of the month, so it's still plenty of time, or the 28th, whenever, 30th, I guess. So there's plenty of time. But you can see here, grammar are broken into categories, okay? So program, ID, ID list of arguments. In this case, input, comma, output. So what does ID list look like? Well, has ID or has ID list, comma, ID. Again, right, that's that recursive I was telling you about, ID list, I can get ID, comma, ID, comma, ID, comma, ID, right? Keep going, right? And this happens to be a left recursive grammar, which is actually not so friendly for top down. And we'll talk about why and how we can fix it, right? And how about the statements? What statement does it have? Well, variable in Pascal, instead of using equals for equality, it uses a single equal for equality. Well, how does it tell then equality versus assignment? It uses a colon equals for assignment. Again, very minor syntactical things. Variable colon equals expression is an assignment statement. Compound statement, procedure call, if statement, while statement, right? Statement itself, in this case, does not have lambda. So that means if statement must have an else. Okay. Okay, so sometimes this else part could be like optional lambda. Okay, not here. Okay, it must have, right? So if it doesn't have, well, there is a lambda here. That means you can have, some parts could be optional. You can have begin and end with nothing in the middle. Well, that's okay. Just put a lambda in. Okay, and then notice the expressions and symbol expressions, and there's term and factor. Actually, this is done this way for operator precedence. Multiplication operators, additional operator, adds and subtract, and relational operators. Those are different levels of precedence. So how does it handle that? It handles that by breaking into different rules. So you can only have add and plus, plus and minus here. You can only have times and divide here, right? That's the only way that's going to work. So you're not going to have an ambiguous grammar. So what does the sample program look like? Here's the program in Pascal. So I think it's note. Again, if you want to work ahead, in Pascal, you need to give it a program a name. So program example, and it needs to have input and output. In Pascal, semicolons are separators and not terminators. So notice the very last statement here does not have a semicolon because it's the last statement. Does anyone? Okay. Functions, and the main is actually way on the bottom. Okay. So begin, end, period is the main. So the main is not on the top. So you got a bunch of functions with the main on the bottom. And this one reads and then writes out the GCD out to numbers. Okay. And so functions, instead of saying return this, how do you return a function value from a function in Pascal? You just set the function name to be the value you want to return. So when you say if b equals 0, then GCD equal colon equals a, this is like saying, well, return a, right? GCD. What's the function? What's the value of the function? A. Well, return it. So GCD equals A, right? So mod is just a modulus function, mod function. So I think you can read this without even knowing Pascal, right? If you've never seen it, it's almost readable. So the only thing I want to point out is the main is at the bottom and the function name is the actual return. That's how you get things returned, okay? So I wanted you to draw me a parse tree. I can tell you the parse tree will take more than one sheet of paper. The parse tree might take like 8 sheets of paper. I had someone like do a plot. It's like this huge thing and turn it in. It's like, okay. Yeah, it's like a butcher paper, yeah. Uh-oh. It's like, oh, I need a magnifying glass to see what's that. Okay. So this I think this is a fun one. And then also when you come back, we need to look at, okay, so now I have the tokens. How do I go about parsing? Well, I need a grammar. The Pascal grammar is not going to help me very much. I need grammar for my language, or we're going to write a grammar for your language. And if you want to look ahead, I have a Lua grammar, a small Lua grammar, and a small C grammar as a starting point. Okay, so that's all I have as far as assignments. Now fill in the 1C. I just want to get that out there. Okay, so I think I felt okay as far as getting information out about the labs themselves in the lab, and then we'll worry about the homework when you come back. Um, I guess I do want to, and I think I talked about, and there's a few other things I want to talk about, then I can let you go tonight. I think I talked about, I think Colin even asked me a lab on Saturday. I think I talked about the white spaces and the fact you have this, this CN with the issue. Lexical analyzer, when it looks at input, it will always go for the longest match. Okay, so as long as you have the rule in there, so if you have 1 plus or 2 pluses, well, it will always go for the longest match. So when you have this greater than sign and a greater than sign where it's actually one operator, okay, it won't get confused. So is that really 1 or 2? For the most part, we'll say, okay, I'm always going to go for the longest one. So it's 2. It's the insertion operator or extraction operator, whatever that thing called. Extraction operator, okay? I'm always going to go for the 2, right? So, and white spaces really doesn't, for the most part, doesn't really make that much difference. I mean, I do need one between the int and the x. Otherwise, I don't know that's 2 different tokens. But if I put 5 spaces or 5 spaces in between the x and the semicolon, that has no effect at all. You should not force the user to actually adhere to a certain amount of white spaces or not. Okay? You cannot expect them to put a space between the open paren, the x, and greater than 5. Okay? Doesn't matter. The way we're doing it with the finite automata, as soon as I hit a white space that's not open part of the open paren, okay, that's done, right? I'm throwing it out. As soon as I hit a white space or not, or like if I'm trying to grab the x out of here, but x greater than sign, that doesn't make into anything. X is an ID, greater than sign is greater than sign. So they're not the same token. They don't go together. Even though there's no white space in between, they don't go together. My finite automata is going to stop as soon as it hits something that's not a letter or a digit or underscore. So it's okay. The way we're doing it, white space doesn't really hurt us, right? I think I talked about, a lexical analyzer will always tokenize everything first. It's fast. Just go through and chop out all in tokens. Then you can decide what to do with it, right? And the only thing that could get us in trouble is, is if you have nested template types. Okay, so, and I think we talked about before you had to put a space in between to make them into 2 tokens. Now you don't, which means the compiler writer, if they encounter this case, instead of flag it as an error, actually has to go back and take the 1 token and break it into 2 tokens. This is a very rare case that will have to do that, right? So you have the tokens in lab 2. We're going to talk about how to do a parser. What comes out of parser is actually this parse tree, which is what you have to do by hand in homework 1. And that's what lab 2 is supposed to do, not by hand, right, in the program. And I think sometimes it's really easy to worry about errors since you know how to program. You know that there could be syntax errors, right? How do you handle that? And who's responsible for handling that? If you have these cases, these are obviously what's called lexical errors or token errors. Although the way we're doing it, just by finite automata, just like peeling off we recognize, like X. As soon as it's a $sign, it says, oh, that's not part of X anymore. Okay, that's just by itself if $sign is allowed. And Y, which is just by itself, okay? The way we're doing it, we're actually chopping off the token into multiple tokens instead of saying, oh, it doesn't look like a valid ID name. Most commercial industry available compilers does handle this differently. instead of just saying strictly just doing, okay, these are the rules I know, these are the rules I don't. They do go back and say X $y. That's not a valid thing. Okay. Well, how does it know that? Then it does have to consider the white space issue. So if you have 32xy, instead of just saying 32 is an integer, xy is an ID, okay, 2 tokens. Right? The errors will pop up later in the parser when you get 32 number and ID with nothing in between. It's not 32 plus, it's not 32. What do? There's no grammar rules that says I can take a number and ID and just put them right next to each other. Okay, that's not valid. So parser will catch it, right? Somebody will catch the error. It's just like, at what point do you catch the error? And if you care about giving user meaningful information, what could that be, right? Is 45B actually allowed? Oh. So I know sometimes you can like put a postfix. You can put like a postfix and saying different number types.
Usually beforehand.
Like before. Oh, so I don't know. At symbol. It is not a C, right? At symbol is not a valid token in C. There's no operator, there's no symbol. You can't use at. Okay, so yeah, that's lexical errors, token errors for the most part. They could all be token errors, but in some cases I may like not process them necessarily as token errors, and that's okay. Right? So what should be caught in a token error? Well, at least the at symbol, if nothing else. That doesn't belong there. I don't have anything that says I can just have an at. Well, what about these syntax errors? X equals semicolon, Y equals X plus semicolon, Z equals bracket, open bracket, semicolon. They're all valid tokens. So, and, great, flying circles. They're all valid tokens, so then I'm sort of deferring. Yes, I can look at this and say that's not valid, but lexical analyzer doesn't know that. It just says, oh, they're all nice tokens. Okay, go into the token list, goes into the token data structure, and the parser gets it and is trying to make sense of what this thing is and is missing stuff. Then the parser catches it, and this is called syntax errors. When we say syntax errors, we are saying, yeah, you're missing something in the parser. Parser is going to catch this. You're missing something that makes it a valid statement, right? And yeah, don't worry about that. Was there another part? Oh, how about this one? Okay, X in X. I ask you to type in something. If X is greater than 5, then X equals quote sharing. Again, tokenizer is going to look at the quote sharing, go string literal token, right? It's not going to even think about it. And the parser is going to get it and says X ID equals expression, a string literal, a constant is an expression, semicolon. The parser is even happy with that. Everybody's happy so far until you get to the semantic analysis. Oh, we can actually see the color this time. The semantic analysis, and that's where it says, wait, look at your symbol table. X is int, which means at parser, when I read that line, it puts X into the symbol table and says you are int. Then when you say X equals, is X declare? Yes, okay. Equals what? Oh, wait, this thing is not an int. And this is where the type tricky stuff comes in, right? This is where the type coercion, type, all this type stuff comes in. What if it's X equals 5.3, which is still not an int, but it's not necessarily a syntax error. You get a warning. You just lose precision. What if thing was declared as a double, but I'm assigning an int to it, right? So they're not exactly the same type. The only thing that requires the same type is templates. Right? Everything else has what's called type promotion. I can take an int and make it into a double. Okay, I could type coercion. I can coerce a float into a double. Okay, so that's all the typing systems come in, which is like research area. It's very complicated. But at least you should do some simple stuff, like a string and end, they don't really go together. Right? So simple type checking, or the fact that X is even declared should be checked. Right? Do I even have X declared somewhere in there? Well, simple table should tell me that. Right? So simple table is used throughout this whole process. And I know this is kind of, oh, okay, there's my graphic. So our class is mostly going to focus on the front end because we just don't have time. We had 10 weeks, now we have like 8. Okay, we just don't have time, right? I'm still going to try to fit all of the important stuff in. And usually an advanced class will focus more on the back end compiler, which means, yep, I know what you have now. So front end deals with you type in something into your .cpp file. I went through all these different processes to figure out what you type. Okay, now I know, what do I do with this information? Okay, so that's where the back end comes in. I'm going to write code. I'm going to optimize it. I'm going to write. And for our project, actually, in this class, we most likely won't take the traditional route, which is dump out assembly and run the assembler through and see if it works. We're most likely going to take the front end product, whatever we come up on the front end, and do something else different in the back end. Like I might take a language written in one language and translate it into another language. Well, I have all the information there. I have my symbol table, I have my parse tree, I have everything there. I can just take this information and dump it out. I can do analysis. I can see if it's you adhere to the coding standards of your organization. Sure, I have all the information there. I could, I can probably do that. Right? I can do.
Can you give an example of something that compares two programs, their functionality, to see if someone's like trying to circumvent like something that, like plagiarism?
Oh yeah, that's actually one of the project options. I had a master's student at OSU who did that for me. And this was back in the day of Fortran. So he actually did a Fortran. So I gave him all of my Fortran class programs, and he run it through a set of measurements. And in order to do that, he had to parse through every single Fortran program, basically, which is the front end. You parse through, and then what he did was something actually quite, wasn't really. I mean, there were some specific measurements in there, like he's counting, I don't know, these complexity measures about, how complex a loop is and stuff. But on the simpler one, he's just counting, right? He's counting like, this program has like 5 different functions. Each function has average number of lines per function, or average variable length and stuff like that. I mean, after you parse through it, you have all that information. And I've always wanted to build one for our 116 class. You can just run all the 116 program through and say, instead of holding up to the light and goes, oh, is this 2 programs similar? Right. So if you move the blocks around a little bit, and all of a sudden they're not similar, but really if you copy the same program, it's the same program. So yeah, there are tools like that. In fact, there's one online. What's it called? I forgot the name. I had to look the name. There's one online in one of the research schools I could just use. I gave them the programs and have them run through the measurements. Yeah, it's a nice compilers project. I think people do like that, right? Running out of time. There's also interpreters as right? Instead of just do the traditional way of compile, a lot of the languages are interpreted. So I don't think we need to have time to talk about history of modern compilers, but Fortran was the very first one. And that's really how started this whole theory-driven, automata, theory-driven compilation. Was that the first Fortran was such a terrible language and a terrible, terrible compiler. So we want to strive for this one pass. So we're going to read the file once and just gather all the information so we don't have to read it again. Wow, okay. So I know I skipped through like a third of this, but I got through this set of slides, like 70 slides. Wow, okay. So now that I've confused you thoroughly, I guess you can go home. Okay, but I will be here on Saturday, 2 to 5, if you need help with the lab. I do have a few more cookies left, so please. Actually, lab is in 207. I don't know why. Lab is in 207.
At least we're on 106.
At least it's better than 106.
On Saturday.